Hey everyone, welcome back to my Calculus 1 series. In today's lesson we'll be going over the limit of a function. So the intuitive definition of a limit will go along the lines of something like this. If f of x is defined near x equals a, then the limit of f of x as x approaches a is L. So we could say that f of x approaches L as x approaches a, or we can read it out loud and say that f of x approaches L as x approaches a. So this mathematical symbol right here is the limit of a function, and essentially we will be analyzing this through multiple different ways, and I will give you a visual example as to what the limit means. So here I have drawn a little graph of this function right here, which is f of x equals to x minus 1 over x squared minus 1. The function goes something like the one in the graph, and I have labeled all of its key points in red. So it has a vertical asymptote at x equals 1, a horizontal asymptote at y equals 0, and then it's got these two key points basically that I have labeled. And this one right here is a hole. If you don't know what that is, you might want to go review, but basically when we have a function and we can cross out common factors, so this would be something like this. We can cross out these common factors and be left with a function like this. The x minus 1, this factor right here becomes a hole. So at x equals 1, we have a hole. But enough with that, and we will analyze this function and look at the limit at 2 points. So let's look at the limit of this function as x approaches 2. Now the way we can analyze this is to look at what point in the graph the y value is approaching as x approaches 2. So we know that somewhere here is x equals 1, so maybe somewhere here is x equals 2, so maybe it's something like this point. Now let's try and pick a point real close to it, something here, maybe something like ff 1.9. If we calculate this, the answer will be 0.344827. And now let's take another point even closer to it, maybe something right here. So this will be f at 1.99. And this will be 0.334448. Finally, if we go even a little bit closer, like super close to the point, f at 1.999, this will equal to 0.3334444. As we can see, a common pattern is emerging, and we can see that all the values seem to be approaching something like 0.33. Maybe it's approaching 1/3. Let's analyze this limit from the other side. So previously we were going in this direction. X was coming from a smaller value and getting closer and closer to 2. But now let's look at the opposite direction. Let's look at x coming from a very large number and down to 2. So what I mean by that is before we were taking values that were smaller than the actual limit that we were looking for, which is 2. But now let's take values that are larger than 2 and slowly get closer to it. So we could start off by taking f at 2.1, and that would equal to 0.322580. And that value would be somewhere here maybe. Now if we were to get a little bit closer, let's say over here, that value might be f at 2.01. And the value of the function at 2.01 will be 0.332225. And now finally, let's get even closer to this point right here. Let me mark it in red right here. And we will choose f at 2.001, which will give us 0.333222. Now again, we can see the same pattern occurring, and it's that this value seems to be approaching this 0.33, or maybe even 1/3. So we can conclude that this limit right here is likely to equal to 1/3. Now going back to the definition of a limit, it's important to note the way it was worded. It was worded that if f of x is defined near x equals a. So now if we take a look at a point like 1 and undefined, which is right here, we can still compute the limit of the function as x approaches 1, even if the point is missing here. So let's go ahead and do that. Following a similar approach, let's take x's that come from the left side, meaning they are smaller than 1 and they slowly approach 1. So f at 0.9 would equal to 0.526316. And if we get a little bit closer to it, we can take f at 0.99, and that would equal to 0.502513. Finally, let's take one step closer and take f at 0.999. This value would equal to 0.500250. Now if we do the same thing and approach this value of x equals 1 from the right side, meaning we are going to take values that are greater than 1 and slowly move towards the left. So we start off by taking f at 1.1. And the value here would be 0.476190. We can get even closer by taking f at 1.01, which equals to 0.497512. And lastly, let's inch a little bit closer and take f at 1.001, which gives us a value of 0.499750. We can see a similar pattern here as we saw in the previous example. Approaching this value of x equals 1 from both sides, from the left side, which is here, and the right side, which is here, they both seem to be approaching this value of 0.5 or a half. So we can conclude by saying that the limit of this function as x approaches 1 is 1/2, even though the point itself at x equals 1 does not exist. So now let's talk about one-sided limits. If we go back to the example that we were previously doing, the way we were computing this limit is taking values from the left side of the value that we were looking for and values from the right side of the value that we were looking for, and we were slowly inching closer. Essentially, what we were doing there is we were taking two limits. We were taking the right-hand limit and the left-hand limit of that specific function. So we can write those as this right here, that the limit of a function, in this case h of x, as x approaches a positive, or we can take the left-handed limit by saying the limit of h of x as x approaches a negative. So a positive means that we are approaching this x value from the right side, and a negative means that we would be approaching this x value from the left side. So let's take a look at this graphically. Here I have a random function called y equals f of x, and we are asked to evaluate this following limit right here, the limit of f of x as x approaches a, and a is labeled right here in red. We can take the right-hand limit of this by approaching this a value with x values that are larger from it. So what this means is we can take an x value here, here, and then slowly inch forward towards a from the right-hand side of a by taking values that are larger than it, slowly inching forward to a, seeing what those values are, and essentially saying that that is the limit. It's the same thing that we've been doing here. We take values that are slightly larger than the value at question, which was x equals 2 in this example, and we slowly inch forward towards the value of x equals 2. So this is called the right-hand limit because we are coming from the right-hand side of a. Now, a left-hand limit would mean that we take values from the left-hand side of a, and that means the values would be smaller than a. And the reason we call this a left-hand limit is because we are coming from the left side of a, and we are slowly inching towards it by taking these x values. Same thing that we were doing over here. We were taking these values right here that were smaller than 2, and we were slowly inching towards it from the left-hand side. So now let's talk about the existence of limits. The definition is as follows. So the limit of f of x as x approaches a is equal to L if, and this double f, like this double IFF right here, just means if and only if. So this limit right here will exist if the limit from the right side, the right-hand limit, and the left-hand limit both equal to the same value of L. If they both equal to the same value of L, then we can conclude that the limit at x equals a is also this value of L. Essentially what this means is that we must approach the same value from both sides. So for a graphical example, let's take a look at these two functions, y equals f of x and y equals h of x. If we look at the value x equals 1 over here, and we also ask ourselves about the limit as x approaches 1 of this function y equals f of x, we can say that this limit right here exists because the value from the right hand side and the value from the left hand side will both be approaching this same value of f of 1, whatever that value is. But as we can see, this graph slowly approaches this value from the left, and from the right it approaches the same value. So we can conclude that the limit of f of x as x approaches 1 will equal to f of 1, because the limit from the right hand side and the limit from the left hand side both equal to f of 1. However, if we jump over to this function right here where y equals h of x, if we are asked about the limit of this function as x approaches 0, we cannot say the same thing about this function. This limit will actually not exist. If we examine the limit from the right hand side, we could see that this approaches something up here, which is whatever this value is. Let's say for the purposes of this example that this value is 2. So the limit of f of x as x approaches 0 from the right hand side right here, this value is going to equal to 2. But now if we examine this same function and approach this value of 0 from the left hand side, we can see that it's approaching this value of, let's say, 1. So the limit of the function as x approaches 0 from the left hand side is equal to 1. And we can see that these two limits are not equal. Therefore, this limit does not exist. So that's basically a graphical representation of what we're looking for if we're going to decide that a limit exists or doesn't exist. There are a few other rules about like cusps and other things, but that we will get onto in later chapters. So now let's move on to limits at infinity. And essentially it's the same thing as a regular limit, except now we're approaching this value of infinity and not this distinct value of, let's say, L. In this case, L will just be infinity. It won't be a number like 1 or 2 or 2.5 or something like that. It will just be the value of infinity. So the definition goes something along the lines of this. Let f be defined on both sides of a. So we do have a left-hand limit and a right-hand limit, except a itself. So not at the value a itself. Then we say that the limit of f of x as x approaches a is equal to infinity if, again, this means if and only if, f of x can be made arbitrarily large. So meaning if we take an x closer and closer to a, f of x will get larger and larger and larger. Likewise, we can say about the opposite of this. The limit of f of x as x approaches a equals to negative infinity if the function can be made arbitrarily small. So if we take an x closer and closer to a from either side, then the value that f of x will have will just be getting smaller and smaller and smaller. So let's go through these examples and determine these limits right here at the bottom. So for the first example, we can see that if we approach x equals a from the left side right here, the value of the function goes towards negative infinity. And likewise, we can see that if we approach x equals a from the right side, the graph goes down towards negative infinity. These red dotted arrows are asymptotes, so the value of the graph will actually never be a, but it will just continue to get closer and closer to that value. So we can conclude that the limit of f of x as x approaches a from the right will also be negative infinity. Now, as we can see, these two limits are equal, so therefore we can conclude that the limit of f of x as x approaches a is also negative infinity. Now looking at this example where y is equal to g of x, let's follow the same protocol to figure out the limit of g of x as x approaches a. So approaching x equals a from the left side, we can see that the graph goes upward and approaches positive infinity. So we can write that the limit of g of x as x approaches a from the left is equal to positive infinity. Now if we examine the function coming from the left side, we can see that it also goes upwards towards positive infinity. So we can write that the limit of g of x as x approaches a from the right is also positive infinity. And because these two limits are equal to each other, we can conclude that the limit of g of x as x approaches a is indeed positive infinity. However, looking at this last example where y is equal to h of x, we can see that approaching this x equals a from the left side, we can say that the limit of h of x as x approaches a from the left side is equal to positive infinity. However, if we examine the graph approaching a from the right side, the value all of a sudden goes downward to negative infinity. So that the limit of h of x as x approaches a from the right side is equal to negative infinity. And we can see that these two values are not equal to each other. So this limit right here actually does not exist. But what we know is that these one-sided limits will always exist for any function because they don't have that strict condition that it has to be the same from both sides, because they are a one-sided limit. So there's no condition on them. They will always exist for any function. So these are the only two limits that we can compute at x equals a for this specific function. We cannot actually compute it at x equals a. We can compute it at x approaches a from the left, and we can compute it from x approaches a from the right, but we cannot compute the limit as x approaches a for this function right here. So now one last thing to note about these functions is that this line right here, x equals a in all these cases, is called a vertical asymptote of the curve, whatever the curve in question is. This one is y equals f of x, here's y equals g of x, and this is y equals h of x. But this line right here is called a vertical asymptote if at least one of these 6 following conditions is true. I'm going to speed it up and write it down here, but basically if we are approaching infinity from any side of this x equals a line, it is considered to be a vertical asymptote. So essentially what I've written here is that if the limit at x equals a is infinity or negative infinity, then that line at x equals a is considered to be a vertical asymptote. Likewise, if we have any right hand limit or left hand limit that approaches positive or negative infinity at the value x equals a, we also call that line x equals a vertical asymptote. So that concludes my introduction to the limits of functions. In further lessons, we will go over how to calculate the limit of a function algebraically and not through this like tedious graphical method. So I hope you enjoyed it. Drop a like and comment on what it helped you. And if you're new to the channel, like, comment, and subscribe. It is greatly appreciated. And yeah, I'll see you guys in the next one.